sorry, this is the input sequence at the receive side. This is the filter, the NMSC filter. This is the desired sequence, the estimate of the desired sequence, and this is the desired sequence. And this is the error sequence. So, in a sense, don't care what is here. Let's say, actually, in equalization, what happens is that here there is a desired sequence, D, that is also the data sequence, D, desired as data, and actually here is the channel with the noise, and this is S. And this D is what we want to recover. But anyway, this is not essential to the problem. The model starts with S and D. Okay? Then in the practice, S is obtained like this. Okay? In equalization. So H of Z is the estimation filter, which in equalization is the receiver filter. Is the sum for k that goes from 1 to L, H, K, Z to the minus K. So it's an FIR filter, finite impulse response of duration L, and it is one causal. Okay? One causal means that starts with Z to the minus 1. Okay, so basically this is the FIR view of that filter. The tab is H, HL, H2, H1. This is the output hat D at time K. This will be SK, SK minus 1, SK minus 2, SK minus L. So hat D at time K is equal to the sum from I from 1 to L, H, I, S, K minus I, which is convolution between H and S. Okay? Also, we impose a stability. That is, we require that the sum of HK in modulus is limited. Let's look to the error. The error at time I is the desired sequence minus half the desired, the estimate. That is the desired minus the sum, and that goes from 1 to L, H, N, S, I minus N, which is exactly what I wrote there. I'm simply substituting. The objective is to minimize the expectation of the squared modulus of the error. We assume that both D and S are jointly stationary sequences. So this expectation will be independent of I. Okay? The expectation is the same, whatever is the time index. Okay? Because of the stationary assumption made on the sequences. So H is equal to the arg min over H of the expectation of the error. The error depends on H here. Okay? What do we know? Of course, we know all the statistical properties of D and S. That is the mean values of D and S, the correlation of D, the autocorrelation of D, the autocorrelation of S, and the cross correlation between D and S. So we have a complete statistical description of the two sequences, S and D. And we must use the statistical description we have of S and D to find the optimum vector H. This is a statistics that depends on the statistics of D and S. Okay? Well, to do this, you see here there is an expectation that will depend on the expectations of D and S. Okay? So, to find the minimum, we make the derivatives and put the derivatives to 0. And we will see that this cost function is of second order, so it has only one minimum. And so we find the absolute minimum with this method. No problem with local minima that can arise in other types of problems as the one that we discussed during the first lessons. Here we don't have the problem because of the square nature of the cost function. So basically it is like a cup, yes, a parabola. Okay? So there is some math about this minimization because we also include in our description the case where the sequences are made by complex numbers. That is, S, H, D can take their values in the complex field. And this is because in digital communication, you know, we always use the complex baseband model. Okay? So actually, when you have a passband signal and down converted to the baseband, you have two signals, the I and the Q signal, the real part and the imaginary part of the complex number. So in this case, we assume that all the variables can be complex. And this puts a little bit of complication because substantially, when I make the derivative, I must make the derivative of the expectation of the squared error with respect to the real part of H, and this is for each value of K, HK, plus J times the derivative of the expectation of the squared error with respect to the imaginary part of HK, and this is for K equal to 1 to L. Okay? So in the end, after some passages that you find in my notes, you come to the conclusion that this is equal to minus 2 times the expectation of the error by the complex conjugate of the signal I minus K. So you put this to 0 for K equal to 1 to L. So you have a system of L equations into the L unknowns that are the H1, H2, HL. Solving the system, you find the optimum H. Now we are going to use the statistical description we have of D and S inside this expectation. Okay, we put D and S inside this expectation, then we perform the expectation and we find the system. Okay, so let us substitute in place of the error this here. So you already have the picture. Okay, I can cancel it. Questions? Any question? Can I proceed? When we put this to 0, I cancel the minus and the 2, which are of course an essential. And what I'm putting to 0 is the expectation of S star I minus k multiplied by the error. And now I substitute in place of the error the I minus the sum for n that goes from 1 to L of H and S I minus n. By the stationary assumption, I can sum k everywhere on the subscales. So this will be equal to Si, the desired I plus k minus the sum for n that goes from 1 to L of H n Si plus k minus n. So simply I have translated all the terms in the product of time lag equal to k. And this can be done by the stationary assumption that we made on the sequences. Now we substitute in place of this product and this product, better, in place of the expectations of this product and of this product, their expectations that are the cross correlation between the input and the desired. You see, this is the expectation of the product between the input and the desired sequence. So this is the cross correlation between the observation, the input, and the hidden sequence. And this is the autocorrelation of the input sequence. You see? Questions? So in the end, we get that this is equal to CSD at time k, SD at time k, plus sum for n that goes from 1 to, this is minus the sum H of course is non-random, it is deterministic, the taps of a filter, the transfer function of a filter, the impulse response of a filter. These are deterministic quantities. We always have to keep in mind that filters are deterministic and mean values are known. Hence, they are deterministic functions. So this is a mean value, the mean of the product. This is the deterministic. This is known. This is deterministic, but it is unknown. And now we are going to find it. And here we have the autocorrelation of the input with the self, which is CS at time k minus n. You see? This must be equal to 0. For k equal to 1, 2 dots L. In other words, we have this system, and 1 to L, H, N, C, S, K minus N equal to C, S, D, K. Put it into a frame and look carefully to that system. It is a linear system in the unknown H. Better, they are L unknowns because N can be equal to 1, 2 up to L. It is a linear system in the unknowns H1, H2, HL with L equations. So there is only one solution for this system. These are called Wiener-Roth equations. Wiener-Hopf. We can write the system in compact form by using vector and matrices. Okay? So C will be the autocorrelation matrix of S. H is the vector of the unknowns, and CSD is the vector of the known terms that are on the right side here. And specifically, if we look inside the matrix and the vectors, what we find is, so simply now I'm writing the linear system in compact form using basically this matrix, which is the matrix of the coefficients of the unknowns. Okay? Of course, you see H is the column vector H1, H2 dots HL to the transpose. CSD is the cross correlation vector CSD1, CSD2, CSDL, and also it is transposed. Okay, are you following me? Problems? No problems? Everything goes easy? Yes, please say yes. No, what is not at this place? Please? No.
I understand, but it's not easy.
It is not. Which is the difficulty? In your opinion? The substitution of the expectation with no? So. If you look right at what I'm writing, it is not difficult. The only difficult passage is, let's say, the algebra behind the derivative with respect to a complex variable that I skipped. I gave only the result, so you can believe it, or you cannot believe it. In that case, you go through Wikipedia or through my notes and you check that derivative. But after that derivative, everything goes easy, because the derivative was here. I brought the derivative inside the expectation because of linearity of the expectation and of the derivative. when you have two linear operators, one after the other, you can reverse them because of linearity. Okay, so I brought the derivative inside and I performed the derivative. And the derivative basically goes from the definition of the hat. In the estimate, there is the h field. I make the derivative with respect to h. So when I make the derivative of a to the square, let's forget by now the complex field. Look to h to the square. I must make the derivative of this one. Well, this will be h by the derivative of h. Okay? And here inside what you find is s, which is independent of h, d and d hat. D is independent of h. D hat depends on h. I make that derivative. And I found this. This term here. This is the error. This is the error, and this is the derivative of the error with respect to h time k. Okay? Now, simply I have to perform the expectation. But the expectations are assumed to be known from the beginning. Remember that in all the statistical methods that we are going to use, we start from the assumption that the distributions are known, the expectations are known, and blah, blah, blah. Everything is known. Even if in many contexts this is not true. For instance, in machine learning, this is basically the difference between machine learning, the theory of machine learning, and the theory of digital communication. They do not assume that the statistics description is given. We are assuming that it is given. So at this point, this expectation is given because S and D are the starting points. And we assume that S is characterized, D is characterized, and also the cross product D by S is known in the mean. Okay? Substitute and I find the system. And that's it. Now let's look to the structure of the matrix. The correlation matrix of the input. This is called a spectral matrix because it is basically a matrix whose entries by rows are CS by columns, CS1, CS, L minus 1. So here there is a windowed version of the autocorrelation of the input, where the window goes from 0 to L minus 1, and then shift CS minus 1, CS 0, CS L minus 2. This is exactly what is written here. I am simply putting this, a set of equations, into the frame. I'm putting them in the form of vector and matrices, but nothing changes. It is exactly the same. These two equations are the same equation. Okay? Simply I'm writing it in compact form. Dot CS 1 minus L CS 2 minus L dot C0. Dots. This will be CS comma minus 1 CS 0. Let's do this. Minus 2, minus 3. CS L minus 1, CS L minus 2. This way. Okay. This is this is called the autocorrelation matrix of the input S. And you see here you have in this column you have the coefficients of the autocorrelation of the input, which is the inverse Fourier transform of the spectrum. So this often takes the name of spectral matrix. And what do you have here? You have basically the same numbers that you have here, but with the shift. So the window shifts to the left, one position. You see? Now you start from -1 and go to L minus 2. So this is a window from 0 to L minus 1. This is a window from -1 to L minus 2. So you take the autocorrelation, look to the autocorrelation through a window and build the first column. Then shift the window upside, or if you look to the autocorrelation this way, on the left of one position and get the second column. Then shift, shift, shift. This is a very special matrix, you see. Usually when you have an, if size is, it is a square matrix of size L by L, of course the size of the problem, okay, to the square. If you have a square matrix of size L by L, usually you find inside L to the square different numbers, while here you always find the same L numbers, because you know CS minus K is equal to CSK to the complex conjugate, the Hermitian property of the autocorrelation. So basically, this is the complex conjugate of this one. You know? This is the basic property of the autocorrelation. Hermitian property of the autocorrelation of the sequence. So basically this is the same as this, whereas the conjugation. So in the end, inside this matrix, you find L different numbers that goes here and there according to the windows that I described before. While generally speaking, into a L by L matrix, you find L to the square different numbers. Okay? Also, all the numbers on the same diagonal are equal. You see? On the main diagonal you have C as a 0, which is the power. The autocorrelation at time 0 is actually the power of the input, and you find the power of the input everywhere on the main diagonal like this. And if you go on this, the second diagonal, you find everywhere CS minus 1. So it is a very, very specific, particular, special arrangement of the autocorrelation inside that matrix. Okay? This leads to some important properties of this matrix that I'm going to list.
Could you repeat how can we find Hermitian property within that matrix?
No, the Hermitian property is a property of the autocorrelation. So it is a general property. It holds before this lesson. Okay, when I introduced the autocorrelation, I said that the autocorrelation is Hermitian. And if I didn't say this now, I'm saying this now. Okay, the autocorrelation is Hermitian. But you should know this from your background. Okay? This is always true when Psi is an autocorrelation independently of the lesson, of the class that I'm giving. Okay? Now what happens is that if you substitute here for n and write the system in this form, you build the CS matrix like this, and you find the FCS minus 1 and the FCS 1. And what I'm saying is, look right, these two are one the complex conjugate of the other because of the general property of the autocorrelation. So psi is an autocorrelation, you see? You are making the product between S and S. And then taking the expectation of the product, which means autocorrelation.
Why do we say that the size is L times L? Because we have L plus 1 columns.
No, we have L. From L minus 1 to 0. From L minus 1. This is L minus 1. So if L is equal to 1, we have only one number. So the size is L. Make an example. Put L equal to 2. You get a 2 by 2 matrix. C0, C1, that's all. Because 1 minus L is 1. Minus 1. It is an L times L system, basically because you want to find L taps of the filters. So L is the size of the filter. And what you get is a system that has L unknowns, that are the taps of the filter, and L equations. And so the matrix is forced to be L times L. Okay? Other questions? Now I'm going to list the properties of this matrix. C is Toeplitz. A Toeplitz matrix is a matrix that has these properties. All the elements along the diagonal are equal. And on the main diagonal, on the second diagonal, on all the diagonals. The consequence is that inversion of C, one of the consequences, requires a number of operations which is in the order of L to L. It is not N, L. L to the square. You know, inversion of a square matrix needs typically a number of operations that is L to the cube in the general case. But this is a very special case, as we said. And you can leverage on the specific form of this matrix, the Toeplitz matrix, to get efficient algorithms for inversion. And we are going to see that now. We are going to invert the matrix to find the optimum age, of course. By leveraging the special nature of this matrix, you can find efficient inversion algorithm that works with L to the square operations in place of L to the cube. Okay? This is one of the consequences of the Toeplitz nature of that matrix. So it is an autocorrelation, so by the Hermitian properties, you write the Hermitian property of the autocorrelation in this way. CS to the Hermitian is equal to CS. What means to the Hermitian? Means transposed and conjugate. Okay? While with the real matrices of real numbers you make transposition, with matrices with complex numbers inside you make transposition and conjugation. You see, when you transpose this matrix, this term goes here and this term goes here. Okay? So they are one the complex conjugate of the other. So transposition and conjugation. Another very important property is that it is positive and semi-definite, like this. If you take any vector x of size L and multiply on the right, on the left, C by x in that way, you always get a number that is non-negative. This property should be regarded as a spectral property. Remember that psi comes from an autocorrelation, and that the autocorrelation is the inverse Fourier transform of a power spectrum. And the basic property of the power spectrum is that it is non-negative. Whatever the frequency you get, you will always get a non-negative number. And here you find the same property. Whatever the direction of the space you look to, you will find a non-negative number. This property, I repeat, is in some sense the translation of the positivity of the power.
How do you relate this x vector to the direction we look? I don't get that concept.
X is a direction. x1, x2, vector x. What is this? Vector. A vector, what is a vector? Is a point, okay? And when you have the origin of the space, the point plus the origin is a direction. It's a straight line. How do you call it? When you have 2 points in a space, a straight line.
You're saying relating this to the spectral. You're saying how
Because,
the
well,
direction you look at
let's
it.
say that this is a more advanced concept. You will need the spectral theorem to fully understand this. But anyway, directions in this space, orthogonal directions in this space, corresponds to the sinusoids in the spectrum. To see this, you must go to the limit for L that goes to infinity. When you go to the limit for L that goes to infinity, you find an important theorem in signal processing that is called the spectral theorem, that relates the orthogonal directions in the space with the sinusoids in the spectrum. But I repeat, this is a more advanced concept. Maybe someone of my colleagues will do this in signal processing, I don't know. It's called the spectral theorem, so it is important. But by the name, you understand that it is important. And basically, to really understand the theorem, you must go to the limit. So you must go to the dense spectrum, where you have infinite sinusoids. So where you have infinite directions in the space. So the size L must go to infinity. At the point you get a reference system in the space that is a set of orthogonal and normal coordinates, and you can show that that set is basically the set of sinusoids in the spectrum. And this is the power of the sinusoid, which is the spectrum, which is always non-negative. I know it is not easy to understand in this way. I repeat, it is a more advanced concept. It is a theorem by the Hungarian mathematician Szego, and we will find another theorem of Szego, not the spectral one, another theorem of Szego during this course. But the spectral theorem is out of the purpose of this course. Even if next year maybe I could add it, especially if you don't see this in other courses. Maybe in the only one that can do that theorem is Spagnoli, signal processing, because it is a typical concept of signal processing. Okay, let's go on. So, assume that when, let's say this is a theorem, so when if x c x is greater than 0 for any direction, for any x, suppose that c is positive definite, not semi-definite. This is semi-definite because it can be 0. Assume that it is always greater than 0 for any x that you get. Then this means that c to the minus 1 exists and that x cx is positive and definite. Basically, this means invertibility of c. When c can be inverted, then c to the minus 1 exists. Okay? And since this is positive, this is also positive. You should look to this pair of equations as to the inversion of a non-negative power spectral density. You see? You have a power spectral density in a range, then it is periodic, can be like this, okay? So, and when you go and invert it, you find something like this. C to the minus 1. This is the spectrum related to psi, and this is the spectrum related to psi to the minus 1. Of course, if you here find a 0, like this, a spectrum like this with a spectrum, you cannot invert. So psi to the minus 1 does not exist. And when you try to invert it, you find infinite here. Okay? A property of c to the minus 1 when it exists is that c s to the minus 1, this is s the signal, is Hermitian. But not tuples. Need not to be tuples. Can be not tuples. But it is Hermitian. You could say, why, if psi represents a spectrum, then also psi to the minus 1 represents a spectrum, which is the inverse of a spectrum. Why, if psi is tuples, psi to the minus 1 is not? There's not this property. Well, because really, you always should take into your mind, bear into your mind that it is a windowed version of the autocorrelation. So this is an effect that is due to windowing. Okay? It is not really an autocorrelation. If it were an autocorrelation, then also the inverse would be an autocorrelation. But it is not an autocorrelation. It is a windowed version of the autocorrelation. And then there are also edge effects due to the finite nature of the matrix. Okay? And this prevents c to the minus 1 to be tuples.
This psi inverse is equal to psi inverse is everything.
Questions? Let's proceed.
Conclude this. Conclude this from
Well, when c is invertible, we invert it and multiply everything on the left by c. Okay? Multiply on the left the two equations by c to the minus 1, if c can be inverted, and find the result. So the optimum vector of coefficients is obtained by the product between the inverse of C with the cross correlation, CSD. And so this is the result. This is the result. You see, you need only the statistical characterization of the input and of the cross correlation between the input and the desired sequence. With these two things, you find the optimum filter in this way. You build the autocorrelation matrix of the input, take its inverse, multiply on the left the cross correlation vector by the inverse. That's it. That's the optimum. That's the optimum filter in the minimum mean square error sense. Whatever are S and D, provided that they are jointly stationary. I didn't assume Gaussianity now. I do not need the Gaussianity now. Why? Because I'm not making the full prediction with the full probability density function of E. I'm only predicting E, and I only want to compute to minimize the mean square error. I don't care about the distribution of it, but only of its mean value, of its variance. And for this reason, I need only mean and variance of the input, mean and covariance and cross correlation, blah blah. Okay? The mean I used the zero mean for all the sequences. I didn't say this at the beginning, but anyway, if there are mean values, then you must put them as in the first lesson, the one about the Gaussian. But anyway, in this case, we are assuming zero mean for the sequences. Okay? Now, let us see what is the performance of the filter in terms of mean square error. Because, you know, you are saying, I want to predict, to estimate the hidden sequence with this S, filtering S through a filter. Okay, I can do this. Okay. Now the problem is, what is the performance that I get? How large is the mean square error? Because if I see that the mean square error is too large, I can decide that this estimate is useless. Okay? On the other hand, if I see that the mean square error is small, then I trust in the estimate. Okay? This is the reason why now I'm going to compute the mean square error that we achieve with this optimum filter. Now, start again from this expectation. We want to know this. And by substituting this vector inside the equations of the mean square error. Basically, this is a square, and as it always happens with the squares, you have three terms. The square of the one, the square of the two, the product between the two. So basically this is H by S minus D, you see, is something like S by H minus plus D. HS is hat D, and this is the desired sequence. When you take the square, you get three terms, this one to the square, this one to the square, and then the product between them. Then you perform the expectation. So, inside here you have these three terms, and outside the expectation. So, the expectation of this 1 to the square. This is S by S by H by H. You see? Now skip the details of vector and matrices. You can find everything where you want in my notes, on Wikipedia, on the books, where you want. Skip all these details, but the very sense is this to the square is S to the square H to the square. S to the square H to the square. Okay? CS is the autocorrelation of S. Is the S to the square in the expectation. H goes out of the expectation because it is deterministic. Okay? And then the special vector matrix structure of the problem is such that you find this quadratic form here. H is a row, H to the H is a row, 1 by L. This is L times L. This is L times 1 because it is a column. Oh, remember, this is one number. We want one number, okay? The performance of the filter is one number, the mean square error. So the result must be a scalar, 1 by 1. This is the expectation of d to the square. If we assume a zero mean, the expectation of d to the square is the variance of d. And this is the cross product, you see? S, H, D. S by D is the statistical part of the cross product. This is the CSD, the cross correlation between S and D. And then there is H, which is this one. Minus 2 times, because here we have the minus and the cross products must be counted 2 times. And then there is the real part, because we are dealing with complex numbers. This is the story of complex numbers. Okay? Now we put this equation inside here. This is the result of the mean square error for any h. Now we put the optimum h here, and we get the mean square error with the optimum h. Before doing this, I must also find h to the Hermitian conjugate. Here this is h. I want h to the Hermitian conjugate, because I need to substitute h to the Hermitian conjugate here and here. Well, this will be cs to the minus 1 csd to the Hermitian conjugate. When making the transposition with matrices and vectors, the product must be switched. Okay, so this will be CSD to the Hermitian conjugate by CS to the minus 1 to the Hermitian conjugate. And now remember the Hermitian property. So CSD to the Hermitian by CS to the minus 1. This is because of the Hermitian property of the autocorrelation matrix and of its inverse, this one. Now we are ready for substitution of the optimum h inside the mean square error. Questions? Questions? Everything is going fine? Okay, let's substitute. Here we have CSD to the Hermitian, CS to the minus 1, and then CS, and then CS to the minus 1, CSD, plus variance minus 2 times the real part of CSD to the H, CS to the minus 1, CSD. Okay? Now look here what happens. I can cancel CS with CS to the -1, and then I can invoke this property for this term. It will be always a real scalar, a non-negative real scalar. So in the end, this is the same as this one, with the -2 in front. Because this is real. So the real part of a real number is that number. And it is also the same number as this one, after simplification of the psi with the psi to the -1. You see? So in the end, this is the variance of d minus CSD to the h, CS to the -1, CSD. This is the mean square error. Of course, this is non-negative, and of course, by that property, this is upper bounded by the variance of the hidden sequence. So these are the two results of the method. These are the properties that you must remember of the important properties of the autocorrelation matrix. The optimum H is obtained by inverting the CS and multiplying it by the cross correlation. When you substitute this into the mean square error, you find the mean square error as a function of the statistical description of the problem that includes the variance of the hidden sequence, the autocorrelation of the observation, and the cross correlation between the observation and the desired sequence. All these numbers, vector matrices are given. So you know which is the mean square error that you will have from the filter, and you also have these two bounds because you get a number from the mean square error. The mean square error is equal to 2. So 2.51. Is it large or small? Well, you can compare it to the upper bound, to the sigma d to the square. If you have a sigma d to the square that is 3, you know sigma d to the square because it is given. If it is 3 and the mean square error is 2.99, you say this estimate is bad, is useless. If you know that the mean square error is the sigma d to the square is a 3 and the mean square error is 10 to the -3, you say okay, it is a good estimate. At the same time, 10 to the -3 can be a large number if the sigma d to the square is 1.1 by 10 to the -3. Okay? So you compare the mean square error that you get to the variance of the unknown sequence. And what results from this comparison says you if the estimate is good or bad. Okay? What is the meaning of the two extremes? That is, suppose that you compute the mean square error and you get that it is 0. You say, okay, ideal estimate. Hat d is exactly equal to d. Stop. I can't do better than this. I am lucky today. Suppose that you compute the mean square error and you find the other extreme, sigma d to the square. You say the estimate is completely useless. What is happening actually is that if we are on this extreme, this means that this term is a zero. Well, all this term, but specifically this one is a zero. Hence h is a zero. So the expectation of ei to the square equal to sigma d to the square means that h, the optimum h, is a vector of zeros. It is the usual old story. When you don't know what to say, please don't speak. Be quiet. Well, actually, how can h be zero given this equation when this product is a zero? But we know that CS is positive, definite. So it must be CSD equal to zero, the cross correlation between the two, because basically this is the spectrum of the input to the inverse. And if we have an input, then we have a spectrum. And so that CS will be always non-zero, basically. You see, here. Here. How can this be zero? Well, of course, if x is a zero. If x is a zero, I'm making the product between a square and the square of zero, which is a zero. The result is a zero. What CSD equal to zero means? Well, it means that S and D are not correlated. If S and D are not correlated, they give you S. What can you say about D? Nothing. I give you S, and then I make a question that is completely uncorrelated to the observable that I'm giving you. Okay? So I'm saying I am Italian, I am 181, I am the teacher of digital communication. Who is the goalkeeper of the Italian team? They are completely uncorrelated. Okay? And based on what I'm saying, you cannot answer. Maybe you know this. Anyway, you cannot answer based on what I'm saying. They are uncorrelated. If they are uncorrelated, then CSD is a zero. If CSD is zero, then H is a zero. If H is a zero, of course, what you say is always zero, and desired minus a zero is equal to desired, and the square of the error is equal to the square of the desired. Okay?
It's not clear to me which part in the formula for the MNC is related to the estimator.
This one.
Okay.
So, this is a property of the hidden sequence. It is not a property of the input, it is not a property of the estimation. This is a property of the hidden sequence. It is the square, the average of the hidden sequence. Okay. Now we improve over it by estimation. This term says you how large is the improvement. The improvement can be zero, then the error is equal to the desired sequence, or the improvement can be full. That is, I have here exactly what I have here, and then the mean square error is zero. So this part is related to the estimation. And you see also this from the passages. What is related to estimation? H. H is the estimator. Okay? The estimator is hat D, which is a combination of S and H, and what we are going to find is H, actually. And you find H here, here, not here, here. Okay? When you substitute for h the optimum, you substitute h here, and you get these two terms, which are actually the same one. The difference is only the minus 2 in front of this one, leading to this term, minus this. So, the error is the input minus what you are estimating in the square. Questions? Now, the example of this is equalization. One of the examples. That is, this is linear estimation. Linear estimation with an FIR filter. You can apply this to many, many problems. One of these problems is equalization, the one from where I started this morning. Because when I think to linear estimation, I always have in mind equalization because I am the teacher of digital communication. But anyway, in other contexts that are not digital communication, you can find linear estimation as well, also if you are not making equalization. In equalization, we call this D with a special name. We call it A, the data sequence. This is G, the channel transfer function. And here we put a delay. Z to the minus delta. This is D. What is that delay? Well, that delay is the delay due to transmission. When I make transmission, I go through a physical medium, and the physical medium puts a delay. So, if I transmit the symbol now, I pass it through the physical medium, I add the noise, then I pass through the equalizer. I cannot ask to have the symbol that I'm transmitting now here, now in this point. It is unphysical. And this is the reason why I am assuming causality of all the systems, of this system and of this system as well. In certain cases, when you are not concerned with the delay, you can remove the causality, simply because you don't care about causality. But in the physical problem, the physical of transmission is causal. And so, I am transmitting the symbol now. I want to see it appearing here after, I don't know, 100 milliseconds. Or what else? After the delay, okay? And delta is the delay that I can accept for the passage of the information through the physical channel and through the physical receiver, okay? So it would be not realistic putting delta equal to 0, because it would be how to say, I transmit now, and I want to know now what you are transmitting from the moon. This is unfeasible. You must wait. And this is what you are waiting. Delta symbol intervals. Z to the minus delta. So let's use the Z transform. A, G plus noise. Here we put noise and yes.
Can you write little bit there because
The sequence and the input is what we are transmitting by the transfer function of the channel plus the additive white Gaussian noise. We assume that N is additive white Gaussian noise. Okay? And D. D of Z equal to A of Z by Z to the minus delta. With delta not lower than 1. Now, these are the two basic pieces of information that I need. S and D, you see? This is exactly the boundary of the system that I studied before. What we know are S, and actually what we know is S, what we want is D, what we know is the statistical dependence of the two and the spectra of the two. Okay? So, CS, the spectrum in the Z domain, it will be equal to CA by CG plus the spectrum of the noise. And what about CSD? Well, it can be shown that this is CA by G star Z to the minus star by Z to the minus delta. This can be shown from the picture, basically, on the assumption that we are making. And this is what I must put after windowing inside matrices and vectors. These are the spectra and the cross correlation without windows in the Z domain, unlimited in time. Okay? You see, these are polynomials of Z. They go from minus infinity to plus infinity in the Z. What you need for the FIR equalization are windowed versions of the two. You need the CS from 0 to L minus 1 and the CSD from 1 to L. So put the windows. So for instance, you can have CSD K like this. This is an instance of CSDK, okay? And you must take it from 1 to L. This is the window that you have on CSDK, from 1 to L, okay? This is the interior CSD. You need only a part of it, a chunk of it, okay? Because you must build a vector if you want to make H FIR. And the same for CS. You will have a CS like this, CSK like this, an autocorrelation. And blah blah blah. And you have to take from 0 to L minus 1. This is the time window you need. That formulas, this one and this other one, are broader than what you need because they give the interior polynomial. You start from this and then make windowing. And then use what you find inside the two windows into the psi matrix and the CSD vector that I give you before. The other thing that you need to know is that this CG, what is CG? CG is the energy spectral density in the Z domain of G, and therefore it is G by G star. Z to the minus star. So, this is non-random. usual, when we want to equalize a signal, we must know the channel. No channel, no party. Okay? If you don't know the transfer function of the channel, how can you equalize? Which means basically invert the effect of the channel. If you don't know the effect of the channel, how can you invert it? No channel, no party. You must know G. You put G here. You find CG. And of course, you must know the statistical properties of the source and of the noise. So, CA and CN. These two are the statistical characterization of the source and of the noise. A and then are uncorrelated. From the uncorrelation of A and then you get this result. When you beat S with D, you make the product S with D. What do you find in say S? Data plus noise. What do you find in say D? Data. The expectation of data by data is data. And then this is the channel, because into S you have also the effect of the channel. You see? So into S you have data, channel, noise, bit with data. Make the product and then the expectation. What do you find? This by this to the complex conjugate, which is data by data, Z to the minus D, the complex conjugate and time reversed version of G. Here is it. And this is data data. What is the expectation of this term by this other term? How large is it? The correlation between data and noise. It is zero. They are uncorrelated. And so here you find only this term, which is data by data delay channel. Data by data delay channel. Okay? And when you make CS, you are making S by S. It is a square. As usually, you have three terms. This to the square, this to the square, the product between them. This to the square is A to the square by G to the square. Here is it. A to the square, the spectrum of A, by G to the square, the CG. The energy spectral density of G in the Z domain. Okay? Then, noise by noise. Here is it. And then the cross product between data and noise in the expectation, it is a zero because they are uncorrelated. Okay? That's it. Usually, very often, we make this assumption, which is also the assumption that will be made in tomorrow's lab. CA of Z equal to sigma A to the square. That is A is zero mean and uncorrelated data sequence. So A of Z IID and Cn of Z equal to N0, white noise, with power spectral density N0, as with power N0 in a unit band. In this case, what happens is that this is a special case. In this case, we have that CS is equal to sigma A to the square by CG plus N0, and CSD of Z results equal to sigma A to the square, the sum over k, gk to the star z to the k minus delta. This is the result for the expectation of the autocorrelation, of the cross correlation, when we put these two assumptions inside these formulas. We get these results, which are typical in equalization. Questions? Specifically, this vector, well, from this term we get the autocorrelation matrix of the input of this S, which is the same form that we already set. For the cross correlation vector, we get a form like this: CSD equal to sigma A to the square by a vector that is G delta minus 1, G delta minus 2, G delta minus L to the Hermitian conjugate. So basically this is a windowed version of the Mitchell filter. You see this one. This is the Mitchell filter, you know? We already said this. And now you must apply the window. The window depends on delta, on the delay that you want. In that way. Questions? No question, no cry. Excellent. Tomorrow you will have the lab about this. Be ready. You have all the afternoon and all the morning to study. You have the material of it. Please study, so tomorrow everything will be completely clear.